How was the exam? Exam was good? Huh? Okay. Okay, so we are coming back to this randomized algorithms. There are something still left. One is called the celebrity problem, and uh, that convex hull I can discuss a little bit more. Okay, the implementation part, right? So if I get the time, I'll get back to that, right? We have lots of things to cover, so we can move on with these randomized algorithms, right? Okay, so in that randomized algorithm section, what we have got that, okay, the Google is trying to interview, okay, Google is trying to interview a number of candidates, and what as an adversary, that means NIT Durgapur, the CDC cell, they will be acting as the adversary, and they are providing the list of the students in such a manner that Google will be forced to hire a number of candidates. We can give the list in such a way, but the Google is also not stupid. Okay, what they will be doing is they will be randomizing the list and they will be interviewing. So that was the main philosophy of that algorithm, that hiring assistant problem. Okay, right. And by this time, uh, one one thing I have noticed that CLRS, the fourth edition is available. Okay, but it is costing little bit more. Okay, but it is colored. Okay, it is colored pictures and all these things. If pocket permits, you can purchase this book costing around 3,500. I don't think you'll be purchasing, but you purchase it and keep it on your shelf. Okay, it will be an asset. Okay, they have they have included three or four chapters. One is this machine learning. One is online algorithm. Okay, one is machine learning, one is online algorithm, and one is this matching. Okay. These are three modern day applications. Okay, three modern day applications. Many of the algorithms we are designing are online in nature. Many of the results we are having as far as applications are concerned, that is utilizing machine learning. And many of the many of the businesses which is happening, maybe Amazon or the Facebook advertisements, whenever they are placing, Google placing advertisements, they can be thought of as the matching problem. Okay. So matching, online algorithms, and machine learning. These are three facets of algorithms right now which we must know to proceed further. Okay. Maybe I am planning to offer one course on modern day applications of algorithms. Maybe uh, in the next semester or so, I can float that as an elective. Okay, where we can discuss many of the modern day problems, modern day algorithms. Okay. Anyway, so we have seen that to analyze that Google hiring assistant problem or the hiring assistant problem, which we have depicted using that using the using this company called Google or whatever, right? So for that we need to have some kind of probabilistic ideas, Okay, that means we need to have idea about probability. Okay. Hello, are you getting? Huh? Getting? You getting? Okay. So in that case, we have got that that probability. Whenever we are talking about probability, we are talking about some sample space. Okay, and then from that sample space, combining the elementary events. Okay, each individual outcome is the elementary event, and combining those elementary events, we are getting our uh, our objective about the big events. Okay, so this event A comprising of these elementary events. Okay, and we are adding up those probabilities because elementary events are mutually exclusive. So that far we have discussed. Right now, in today's class, few more things we need to discuss. One is this random variable. One is this random variable. Okay. So this random variable is very important. Random variable, right? And this random variable is at the heart of analysis of this randomized algorithm. Okay. So that's why we need to learn this, and also whenever we are dealing with any probability course, this random variable will be coming into picture. Okay. But maybe what I have seen in 10th, 12th standard, whatever is depicted about probability at that time, this random variable and expectation is missing, but which is very important. Expectation of random variable of RV. So this is random variable RV. This expectation of random variable, that treatment is somewhat missing. Okay, but anyway, we'll be discussing a little bit about this random variable and this expectation, which will be required for further proceeding. Right now, so far we have discussed event of interest out of an experiment in an ad hoc manner. Ad hoc manner, say we are looking for these two coin flips we are having, and we are looking for that the event A that is comprising of at least one head. Okay, that is the event we are looking for. At least one event, right? Or exactly one event. So sorry, at least one head or exactly one head, right? So exactly one head. Whenever we are flipping two coins simultaneously, then what we can think of that okay, this event comprising of HT and TH. Okay, so this event will be depicting the fact that we are looking for one head, one head, that event of interest we are having, and that is we are comprising from that sample space. Okay, which are the elementary events satisfying that condition that we are having exactly one head. So HH will not be satisfying this because it is having two heads. Okay, so this event of interest, okay, we are defining in an ad hoc manner. Okay, now the question is there any systematic way of representing event of interests, and which will be very much essential for developing some kind of theory about whatever we are discussing about randomized algorithms or probability in general. Okay, the answer is yes, and that answer is yes because by random variable it is generally represented by random variables by introducing this concept random variables with one go by defining one variable. Okay, as whenever we are uh, discussing about any programming language. Okay, so at that time what we do, we are defining some variables, say some and that some might be having value say 1, or some might be having value 2, or whatever, say 3.2, something like this. So that's why this is a variable. Okay, it can take more values. It can take many different values. Now here also this is associated with a word called variable. Okay, we are defining this by say x, capital X, or say y, capital Y, or say capital Z, something like this, or say capital O, or say capital B. Okay, so we'll be mainly discussing about with the help of X, or say X sub I, or Y sub I, and Z sub I. Okay. Now this X is a variable. Okay. And this X can take many different values. Many different values. X can take 0, X can take 1, X can take 2, and so on. Okay. Depending on the application we are discussing. Say we are discussing about the application 2 coin flips, right? 2 coin flips we are having, and at that time we are looking for number of heads. Okay, so if I am associating x equal to 0, and this x is random because it can take any of these values randomly, 0, 1, 2. Okay, because whenever we are flipping coin, so which values will be coming, we don't know. Okay, so that's why it's random variable. Okay, that means in probability parlance we are discussing variable. It can take value 0. That means this x equal to 0 will be denoting one event, say a1, one event. X equal to 1 will be denoting another event. X equal to 2 will be denoting another event. Okay, right? And we are looking for the events, that is number of heads, right? Whenever we are flipping 2 coins simultaneously, say. Now x equal to 0 means what? X equal to 0, number of heads. That means what is the outcome we have got? We have got that it's TT. It's TT we have got. That's why it is x equal to 0. Heads, number of heads 0. Okay. X equal to 1. That means we are looking for exactly one head. So which are the elementary events that will be comprising this? So this guy, HT and TH. So x equal to 2 will be depicting another event, and that is 2 heads, HH. Okay, so this event x equal to 2 will be comprising of this set, x equal to 1 will be comprising of this set, x equal to 0 will be comprising of this set. Okay, so at one go. So previously we had to declare for uh, everything in an ad hoc manner. Okay, we are wanting exactly one head. Okay, but we are capturing that idea into some variables so that our life might be very easy. Okay, so that's why this at one go with the simple variable x, we can denote many events of interest. So that is the sole idea of having this random variable into our parlance, right? Okay. Next, okay, so whatever we have discussed is written over here. So x equal to 0 depicts 0 heads. That means that will be comprising of elementary events TT. X equal to 1 depicts 1 heads. That is, that will be comprising of this, exactly 1 head. And x equal to 2, 2 heads. So that is comprising of this elementary event HH. And we had the sample space So this HH, HT, TH and TT, whenever we are flipping two coins simultaneously. And out of that we are looking for number of heads. And with these values, whenever X will be taking these values, each one will be corresponding one event of interest. So this is the main idea. Okay. Now, so this X equal to 1 is comprising of HT and TH. Okay. So what we are doing, X equal to X, we can think of this X is a function that is mapping this event space into a number. Okay. So this elementary event, whenever I am passing, it's satisfying that okay, number of head is 1, so it is 1. X is TH. If I pass TH, then also it will be 1. So that's why this X equal to 1 comprising of HT and TH. But if I pass X equal to HH, then it is mapping to the number 2. Okay, right? So it is not satisfying X equal to 1 case. So HH will not be included here. Okay. So now what we can say after having this discussion, what we can say is probability X equal to X. Probability X equal to X. Okay. So that will be comprising of what? So X equal to X comprising of all the elementary events which will be satisfying X equal to X case. Okay. So this X small x could be 0, could be 1, could be 2 for our example. So if x equal to 1, we have seen that it is comprising of ht and th. Okay. So this probability of x equal to x, then what we can say by our mutual exclusiveness property, that it will be probability of the small s, where s will be belonging to this x, where s will be belonging to this s, capital S, such that x of small s is equal to x. That we have seen in the previous case. X of this small x, x of this small s will be this x, small x. So this is this is for x equal to 1 case, where this probability ht is small s, that is ht, that is small s, again this is small s. So s, that small s will be definitely belonging to the sample space. That is the criteria, such that that small s will be mapped to this number of interest, 1. Okay. So that is the way we can define this x equal to x, its probability. Okay. And this is quite logical, right? This probability x equal to 0, so that will be probability of tt, and probability x equal to 2, that will be probability of ht. And now probability of ht, if I am having two coins flipped simultaneously, what will be the probability of ht? 1 by 4. So 1 by 4 is written. Out of 4 favorable case, we are having 1. For 4 outcome, we are having 1 favorable case. And 1 4 for probability of th. So then it is becoming half. And probability x equal to 0, it's 1/4. And this probability x equal to 2, it's 1/4 again. Right. And this the probability x equal to x, that we are denoting by this fx, and it is probability density function of that random variable under consideration. Okay. And if we add up all the probabilities by putting all the values of small x, then that will be becoming 1. Because you see that whenever we are flipping two coins simultaneously, what are the values of x? X could be 0, x could be 2. That means this small x could be 0, could be 1, could be 2. Okay. So probability of x equal to x. So that means that this summation, if I expand for our application, then it will be probability x equal to 0 sorry, plus probability x equal to 1 plus probability x equal to 2. Okay. And this probability x equal to 0, we have got it is 1/4. X equal to 1, we have got half. And x equal to 2, we have got 1/4. So what will be the value of this? 1. So that random variable under consideration, if we add up all the values of this x, small x, so that will be giving us this one, which is satisfying this probability axiom. Okay. Now another thing that we got to understand is this expected value of this random variable, which is very, very important. Okay. The 70% analysis of algorithms is based on this expectation of random variables. Okay. And it's if I am taking it's a little bit more on this expected value of random variable. Okay. That more, what kind of thing that means? We should be having this tail bound of this random variable, that comprising of Markov inequality, Chebyshev, Charnov bounds. So based on that, the 70% analysis is done in computer science. Okay. Even if you are not having any kind of probability associated with your algorithm, but we can transfer that into probability space and we can analyze. And people in an ad hoc manner exactly doing like this. Whether he is from IISc or he is from Stanford, he is from MIT, okay, or he is from Princeton or Hebrew University, Jerusalem. Okay, so this expectation of this random variable we need to understand. Okay, so we can understand this with the example that with the running example we are having two simultaneous coin flip. Okay, and say we are interested in the expected number of heads in our flipping of two coins experiment. Okay. In other words, out of two coin flip, on an average, how many heads we are expecting? Okay. Two coins we are flipping, or we can think of this is the similar experiment that we are flipping coin one after another. Okay. The same experiment. So say if you are flipping say 100 coins, how many heads you are expecting? Expecting. Hmm? Yes. 50. 50. If that is not the case, if then that tossing scenario will not be coming in cricket match to fix who is going to bat first. or who is going to bowl first. Maybe this Australia is coming to India touring. Okay, at that time, say if in Indian condition, if we know that if we are batting first, then we're going to win. Okay. Maybe the fourth innings is absolutely the batting side will be having some devastating effect. Okay, maybe you can bowled out by 50 runs or so. Okay, so if I'm thinking that okay, whenever I'm flipping say 100 coins, and at that time I'm expecting okay, 50% of the time I'll be having heads. Okay, 50%. Then okay, if two coins I'm flipping, then one I'll be getting head at least. Okay, so that may be the expectation. That the expectation means average value of that random variable. What average value that random variable can take? We have seen that random variable. If I am looking for the number of heads, we have seen that random variable is taking 0. It can take 0, 1, 2. Okay, but what is on an average? What we can take? That is exactly we are looking for here, right? So let us analyze this scenario. Any question? So let us analyze that scenario. And here, what the way we define this expectation of x is like this. Expectation of x is summed up over all x, that whatever this x small x in our example it is x equal to 0, 1 or 2, and what value I am having, and that value will be weighted by the probability of having that value. Okay, the weight of this, so this how much weight I can take this, that will be decided by this probability. Okay, we are defining the expectation in this way, and we are looking for here this discrete random variable. That means it's not a continuous one, as in our coin flip experiment the value x can take value 0, 1 and 2. So all these values are discrete. We are not telling so far that okay, this x can take value 0.1 something. Okay, then we'll be discussing about this continuous domain. And in continuous domain, we are having many applications. But as far as computer science is concerned, we talk about it's all about counting problem. Computer science all about, and that counting is heavily fitting in this discrete scenario. Okay, so that's why until stated otherwise, we are talking about discrete random variable. Okay. So this is the definition of this expectation. Now, with this definition, let us find out that expected number of heads whenever we are flipping two coins simultaneously. So at that time, what we got to do? So expected number of heads. Number of heads I am defining by this random variable. We have to come up with the idea that x can take what values? Sorry. It can take 0, it can take 1, it can take 2. Okay, that we have seen. And then I'll be fitting that into this definition. Expectation of x is equal to summation over all x times its weight. Probability x equal to x. Okay. So now I am putting this value. X I know it could be 0. It could be 0, this x. And its probability x equal to 0. Plus then 1 times probability x equal to 1 plus 2 times probability x equal to 2. Okay, so we have got this. Now 0 times whatever I am putting, it will be 0 plus 1 times sorry, what we have calculated about probability x equal to 1, 1 by 2. Already we have calculated that x equal to 1 and plus 2 times what we have calculated, 1 by 4. So this is half plus this is half, that is equal to 1. So expected value is becoming 1. Okay, and then we can have some kind of this thumbs up. Okay, right? So whatever we were exactly looking for, we have got. So this expected value, that means 2 coins I am flipping simultaneously. One of the times or on an average you will be getting 1 heads. Or if I am flipping 100 coins, then I'll be getting 50% of the time the heads. Okay. There is an analysis that called streak problem, that if say Virat Kohli is going for toss, okay, and then he is getting head, or he is getting tail, and then next match he is getting tail, next match he is getting tail. Okay, next match he is getting tail. Will this be happening continuously on and on? He is getting tail. Okay, then BCCI will be telling, no, this is not the good way of deciding. Okay, so there is a strict problem that analyzes that, okay, this, if I am flipping n number of coins, okay, then maybe log n number of times, starting from any iteration, log n number of times we can have this exactly tail 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 or head head head. Okay, this is called the streak problem, and log n is a very small number. So this tail 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 is absolutely absurd. Okay, right? Okay, so today up to this, and in the next class what we'll be doing, by using another 2 concept, we'll be coming back to this analysis part of hiring assistant problem.